doing the social distancing thing, and so I try to keep myself active with things like road cycling and mountain biking. But right now, all of our mountain bike areas are shut down, and we've still got snow in the mountains. But again, we finally got rid of the last bit of ice and snow in my yard, so I'm starting to do relief raking. So I've got a few blisters on my hands from that activity, even though I'm wearing gloves. So let's get into the oil sampling part of it. What to sample? Where can we be taking samples? Let me get my laser pointer moving here. Okay. Incoming oils, brand new oils coming in, regardless of kind of what size of container you're using to receive those in, whether they're drums or totes or truckloads. Certainly if they're drums, you can't sample every drum that comes into your plant. There's just too many. So you may want to sample some random ones. And I have a short list here for what to test for. I want to be sure that those incoming oils are clean and dry, so particle count and water. I want to be sure it's got the right oil in the drum that pertains to the label on the drum. So I want to check the viscosity. I may actually get into checking some additive elements with a spectrometric analysis, just to be sure it's got the right fingerprint of additives and I've got the right oil. If oils have been in storage for a while, we may want to take, and by a while, let me say a couple of years, I may want to take some samples of those containers and just be sure that the additives haven't stratified and any contamination hasn't gotten into those oils. And again, that's going to depend a lot of the contamination on where the containers have been stored. Are they outside sitting exposed to rainwater, or are they in a storage room inside a plant where they're temperature controlled and not exposed to the elements? Used oils in service. This is where we mainly think of doing oil analysis and taking samples off of critical equipment. So again, this is the most common use of oil analysis. We could also take samples from after reconditioning an oil. So if in the plant we've put a filter cart on a piece of equipment and tried to clean it up, we may want to take samples before and after so that we can see how much we've actually cleaned up that oil and what ISO count we've got, or water content. Or if we've actually hired a commercial vendor to come in and clean up a larger reservoir, I'd want to take samples before, tell the vendor what condition the oil's in when he comes in, and then have a target that I want the oil cleaned up to, certain ISO code, certain water content. So those are the kinds of things where we can take samples and use oil analysis to help us control some of our processes. So sampling locations from equipment. Up at the top, I've got a sampling port, just an example of one up there, and this is probably your best option for trying to grab a sample. This is going to be located in a flow line, and we're going to talk later in the course about where to locate these and get our best samples. Next option, second choice, might be to use the plastic tube method with a vacuum pump on it, a hand-operated vacuum pump, to pull a sample out of a dipstick hole or from a vent breather in a piece of equipment. Worst case scenario, down at the bottom, a drain plug sample. And the reason I'd like to really try to avoid those is because there's dirt and grime on the outside of the plug and on the outside of the sump. This looks like an oil pan. This picture, an oil pan from a car or a truck or something. So there's contaminants on the outside that could get into our bottle. There's also going to be sediment on the inside of that oil pan that's going to get carried out with the oil and get into our oil sample. And what we're trying to do is get a representative sample of oil, not a best case or a worst case. So again, taking this drain plug sample is going to be a worst case, and it's not really representative of what oil we're likely going to see in our equipment, going through the contacts of bearing contacts, gear contacts, hydraulic pumps, and such. So let's just talk about sampling from different types of pressurized systems: a non-pressurized, a low pressurized, and then a high pressure system, and just the type of equipment that we may need to use that. So again, we're back to our plastic tube and the vacuum pump if there isn't pressure in the system. So if we're going to go down through a dipstick hole or something like that to grab a sample, we need to draw the sample up into our sample bottle. We need to create a vacuum, and a common pump like this is used to do that. And just a couple of other pictures of them on the right-hand side. Once we get into a low-pressure system, So a picture I have here is taking a sample off of an engine where we're using the engine's running. So we've got the oil pump running, we've got low pressure being created here, and we can grab a sample from a sample port. And this is the type of port that we might use up at the top here. And inside those, this type of sampling port that I'm pointing at, there'll be like a check valve in there, a ball held against a seat with a spring. And so when you connect onto it, as this guy's doing to grab this sample, there's a male portion of this that's going to unseat the ball and allow oil to flow out under this lower pressure directly down into our sample bottle down below. There's different variations on this. Up in the top right-hand corner, got a type where you actually put your thumb on this, push it in, and it does the same thing. It opens up a check valve inside and allows the oil to flow out and down the bottom here and into our sample container. When we install these, and we'll see examples of this as we go through it, but preferably on an elbow, right angle elbow, so that we get a little bit of mixing and turbulence in this oil before we actually take our sample out into our bottle. So that's low pressure. As we move to higher pressure systems, so maybe you want to take a sample from a hydraulic system that's operating at 3,000 psi, and you want it out of one of the flow lines where the oil pressure is fairly high, we need to install some sort of a valve in there. So just this valve, this ball valve up top here with a coil on it, just so that we can throttle the flow and we don't suddenly open up a flow at high pressure and hot oil, and you'll find that we've got a safety issue that we're dealing with. With a valve here, we can open this up gently and allow the flow to come out very controlled into our bottle. So that's what we want to try to do in a high pressure system. How full should the sample bottle be? I've got some examples here. We talk about some lower viscosity oils and ISO 32 being about 3/4 full. Then as the viscosity increases, we're filling the bottle to a less extent, more airspace above with higher viscosity oils. My main comment is I want some airspace in there. Okay, whether you stick strictly to these guidelines or not, but we do need some airspace in there, because as soon as the sample is being taken, particles start to settle. So particles will start to settle to the bottom of our container. It goes into the lab. They're going to agitate this sample, maybe on a paint shaker, so something very vigorous, and they need some airspace up above to get the oil moving around enough to resuspend the particles that are down below. And you might think, well, what if I just fill it right to the very top and the lab can simply pour some oil off the top of this bottle? There's a problem again. Particles have settled, your particles are concentrated at the bottom, and you think, well, if we just pour oil off the top, but now you're pouring a cleaner oil off the top, and you're changing the concentration of the particles that have settled to what you're pouring off the top. So you've changed the ratio of all your materials inside, especially your solid particles. So we want to leave some airspace. That's the main message there. Sample bottles, I'd like you to obtain them from the laboratory, especially so you're dealing with a commercial lab. You're going to get your sample bottles from the laboratory. Okay, and if you're obtaining them, if they're purchased for an on-site laboratory, purchase from a supplier who already supplies a commercial lab. We want bottles that have been pre-cleaned, and we'll talk about the cleanliness level just down at the bottom. I prefer to have a clear bottle. The plastic bottles work nicely. I still like to have a clear bottle because I like to see the oil that's inside. I know it's not very scientific, but it gives me a nice, warm, fuzzy feeling if I see an oil in the sample bottle that's nice and clear, as opposed to one that's kind of murky and discolored.
Well, just a point on that. It depends on the test. You're right. For 90% of all the lab tests, that's fine. But if you're going to do the ASTM test for varnish, you need to use a non-clear bottle, or put it in a container or cardboard sleeve right after you're done.
Mm-hmm. If you're doing the membrane patch colorimetry test, there's a specific bottle for that because it is affected by storage and its sensitivity to light. So very good point, Peter. And apparently phosphate esters are preferred in glass. The only problem with glass is, again, if you drop it, it breaks. So there's the only downside of using a glass container. And for shipping purposes, they're a little bit heavier, but that's probably fairly insignificant. I did read some comments about plastic containers allowing light hydrocarbons to diffuse out. So if you were trying to do a flash point from fuel in a diesel engine or something, plastic containers could allow some of those hydrocarbons to diffuse out. I'm not sure how serious that problem is. Down at the bottom, I list some of the specified cleanliness levels for bottles. We have ultra clean, and it's allowed, so that bottle, just the bottle itself, one particle greater than 10 microns per milliliter of volume of the bottle. As we go to super clean, there's 10 times more allowed. And as we go to what they refer to as a clean bottle, 100 times more particles allowed. The ones that are typically used by most commercial laboratories are the super clean bottles. Okay, so that's what you should try to obtain and get from those. I make a comment down here at the bottom, don't buy your bottles from your local hardware store. I have had people mention that to me, that, oh, we buy our bottles at, again, the hardware store down the street because they're really cheap down there. But the problem is they're not clean. And that's probably okay if you're just doing a viscosity, maybe an acid number or something like that. But if we're going to do any particle counting, which is quite common, we want a bottle that's clean. We don't want the bottle contributing to the particle count numbers that we're going to gain. So let's walk through some different types of equipment and see where some options are for getting samples off of here. So here we've got a standalone gearbox, okay? There's no circulation here. It's a wet sump system, and we've got some sediment at the bottom of this. There's our oil. Our gears are rotating. So we've got 1, 2, at least 3, and then over on the right-hand side, a filter cover. We've got several options here. And I've tried to rate them as the sort of good, fair, and a worst-case scenario for these, or the good, bad, and the ugly for trying to where to take these samples. So let's start down at the very bottom, this drain plug or drain port sample. I've given it a C, a poor rating, for the same reasons as I mentioned earlier. The sample valve at the bottom has probably got dirt and grime on it, and inside there's probably a layer of material, water and sediment in there, and some of that potentially gets into our sample bottle. The lab analyzes it, and now we get a misrepresentative sample, and we're going to get results that are much worse than the typical oil going through the gears and bearings. So this is not a good place to grab a sample. I'm going to go up to the top and say, grab the one with the plastic tube. So we've inserted a plastic tube down through a dipstick hole or a vent. Again, there's no pressure here, so we have to pull a vacuum on that sample and pull it over into our bottle. One of the problems with this plastic tube is, first of all, the tubes come coiled. So as you put it down inside, my diagram here is as the tube stays fairly straight, but the tubes are coiled. You put it down through that hole on the top, and the tube will simply start coiling around. And so sometimes it's very difficult just to get the end of the tube anywhere in the oil at all, and you're happy when you get it in the oil and you can actually pull some vacuum and pull an oil sample over into your bottle. But the problem is we're never sure where the end of that tube has been. When we pushed it down in here, first of all, you got to shut the gearbox off, but we send the tube down in here. Did it scrape up against the sidewall? Did it go down through the sludge and material at the bottom? And we're never quite sure, again, where in the oil it is. So we're not going to get a consistent sample from this drop tube, as some people refer to it, or this plastic tube. What we prefer to do is grab a sample from a fixed piece of tubing off on the side here. So let's assume that this drain port at the bottom does not exist, and that we've had a port on the side that's been our drain plug for years. So we've had a valve out to the side. We've been able to drain the oil off of this. So the sludge level has built up basically to the bottom of that drain port. What we're going to do is we're going to take that existing one out, and we're going to insert a new fitting in there. I'm just going to go to the next slide for a second and give you a bit of a close-up of what this is going to look like. So here's our nipple that's threaded into our gearbox, and running down the middle of it is a tube. And it runs right out to our sampling port here. We could put a ball valve or something on the bottom so that now we haven't lost our drain. We can still drain oil out the bottom, but now we have a tube running right down the middle of this that we're going to grab our sample from. Let me go back to my gearbox. So that's what I'm trying to depict down here at the bottom. Okay, so that works quite well. You'll notice in my diagram, I curved the tube up. at the very end. So I've got a slight curve, so I'm sitting up at the end of it up here. And I've done that specifically to stay away from any sludge or material, sludge, water, debris that's sitting at the bottom of this gearbox, because I don't want to be on the interface between the oil and that sludge, and again, be grabbing a worst case sample, because that's not representative of what's going through our gears and bearings. So I've given this an A. That's probably, we're taking the sample from the very same place every single time, and good place to grab a sample. Let's go over to the right-hand side. Some people will sometimes bring a filter cart over to a piece of equipment, hook it up, start circulating the oil out, and try to grab a sample out here. Now, if the filter cart was attached to this gearbox full-time, 24/7, always on, always attached to this one box, then grabbing a sample out here off of this filter housing, this is going to be after the pump, before the filter. This would actually, I'd give this an A, actually, if this was on full-time, if the filter cart was attached to the gearbox full-time. But that's not normally the case. Normally, this gearbox is a standalone gearbox. We're going to bring this cart over from another piece of machinery. We're going to hook it up here, put power to it, turn the pump on, and start circulating oil out through this filter cart. Okay, and if we grab a sample out here, what I'm concerned about is the cross-mixing ratio. How much oil is sitting out in these lines? We could potentially bypass the filters, but how much oil is sitting out in these lines, the pump, compared to the oil in the sump? So I've given it two different ratings down here. One, if the cross-contamination ratio is low. So let me just throw some numbers out here. What if I had a, we could talk in liters or gallons, but the ratio's irrelevant here. If I said I've got a gallon of oil sitting out in this piping out here, and I have 50 gallons in my gearbox, I would have a 1 to 50 mixing ratio. Probably not that good. Or if it was 1 to 10, I would consider that unacceptable. But if I have a gallon of oil or several, whatever the liter which might be out here, 4 liters of oil out here, and I had 100 gallons of oil or 400 liters of volume in my gearbox, or a full drum, something like that, then my mixing ratio is fairly low, and I'm probably not as concerned. So again, depending upon how big your sump is and how much cross-contamination that ratio is, might dictate whether I would give this a B or a C. But it's less than ideal. Again, I'm going to point you back toward this sampling port over in the bottom left-hand corner. There was, again, the picture of that sampling port. Okay. What about a...
Bob, sorry, there's a couple questions coming in.
Okay.
And, I wasn't sure when to ask them, so if you could go back on your slide. Okay, can the oil sample be taken from that gearbox when it's running, or does it have to be shut down?
Prefer it to be running, okay, so that we're getting proper mixing. But if you're using this plastic tube, you're not going to be able to send the tube down with the gearbox running, because you know what's going to happen. The gears are going to grab that tube. You're going to be on one end of it. The gears are going to be on the other, and I know who's going to win that battle. It's going to get sucked into the gearbox, and now you've got plastic bits in your sump.
But we have a second question. Sorry, and I'm not sure your expertise in gearbox in particular, but here's the question: in cooling tower gearboxes, how can we take the oil sample when we only have makeup line available where there's dead oil present?
One of the problems with cooling tower gearboxes is the volume can be fairly small, and it's very difficult to get a sample out of them unless you install a separate sampling port. Now, I know from my past days of teaching courses, one option was what they referred to in the past as micro bore tubing. So the tube that you're going to grab your sample from has a very low volume internally, so that you minimize the amount of oil that you have to actually flush and throw away, so that you don't alter the oil level in that gearbox very much. Try to take as little sample as possible, a little flushing as possible, so you don't alter that level. Think that answers the question?
That answers the question. Thank you.
Okay. So let me just move on here. So here I've got a gearbox or any system. I say up here it could be a circulating gearbox or an engine, works the same way, where we've got our piece of equipment that's operating. We've got a sump down below. We're going to pull oil off through a pump, up through a filter, and circulate it. So you could replace this diagram with an engine if you want. Okay. Primary sampling point. If you could only sample one spot here, where's your best place to sample? And it's after the pump and before the filter, and preferably on an elbow to, again, gain some mixing. So at the very bottom is a cutaway of one of these sampling valves. So you can see the ball that's in there. There's a spring in behind it. The cap is on the top, so we're going to remove the cap. We're going to put a male fitting on here that's going to push the ball back against the spring and allow oil to come out. Now we're at low pressure here, so again, this fits with what we said earlier about low pressure. We're after the pump, before the filter, because we're looking, one of the main things we're going to look for is wear debris, and we want to catch it off of our gears and bearings, but this pump is also critical. If this pump fails, the oil doesn't circulate, and we're going to lose lubrication to our gears and bearings. So the pump's as critical as the gears and bearings. So we want to see if we're getting any wear debris off of that. So again, after the pump, but before the filter, because the filter potentially removes some debris that we're looking for. So that's the logic of grabbing it there. Engine, oh, sorry, I jumped one slide too many. So here's again, just a diagram of one of those valves, and we've installed it on an elbow so that we get some mixing as opposed to a linear piece of pipe here, okay? And what we're trying to avoid with the linear piece of pipe is laminar flow, where we could get some particles that settle out. If we catch it right on an elbow, the oil's got to make a right-hand turn, and that gives us some turbulence and potentially gets us a little better sample. What we want to do with sampling for sure is consistency. I can't think of another word in oil analysis that's more critical. We want consistency in our sampling. The sample has to be taken exactly the same way every single time. Okay, so that was, I put this in just to illustrate again what we're showing down in this bottom corner of where that sample would be taken.
Bob, can I interrupt you for a couple more questions, sir?
Sure.
Is there a specific test you recommend the ultra clean containers for, or where would you use those ultra clean containers?
The first thing that comes to my mind, high pressure hydraulics. 5,000, 10,000 PSI hydraulics, where we're going to have piston pumps with fine clearances. We've got likely servo valves with fine clearances. So we're going to be, our ISO particle count numbers are going to be very, very low. And so we need a very, very clean bottle so it doesn't affect our particle count results. So high pressure hydraulics would be a classic one.
Okay, a second question for you. Is there a brand name of valve you recommend, or is there a number of, there was a question specifically on the valve you were showing on the screen. Where do you usually get those valves from?
I'm not aware of any specific brands. Some companies have been bought and sold over the years. I think there's a company by the name of Trico that sell these, and I think they're an international company, so they should be available. So that's TRICO. If you just Google search that, you'd come up probably with the Trico Corporation or whatever their official title is, and they sell a number of pieces of equipment like this. I've heard this referred to as a Stauff valve or Stauff valve, STAUFF, but I'm not sure if they still exist. I'm just not sure. They might have been bought up by Trico. That kind of thing happens. So sometimes, again, names change over the years.
And the last question is, why are you taking the sample from that elbow location there?
To get some mixing, to get some turbulence.
Okay.
Okay, I'm simply trying to get the oil as it goes around this corner to create some mixing and turbulence here, just to try to get a better sample out into my bottle, as opposed to on a linear piece of line where we've got laminar flow. Particles could settle because in laminar flow, the oil flows down the middle of the pipe much faster than it does against the walls of the pipe. So we're just trying to get mixing. It's just, I know it sounds picky, but we're just trying to get a little better sample, a little more consistent sample. Okay?
Sure, go ahead.
And
Hello, sir.
this is a bit of a repeat, but in engines.
Hello?
Sorry, could I ask that all questions be asked via the chat window, please?
Okay. Engines, similar to that gearbox that we showed, we've got a pump that's going to grab oil from the sump and circulate it out through a filter assembly around the engine, and the oil cascades back down to the sump of the engine. So we've got a few options here. The option at the top here is to take it from a sampling port off the filter housing. That's our best option. Second choice, if you didn't say with a passenger car, which typically would not have a filter housing like this, you could send a tube down through the dipstick hole, but again, engine can't be running, and you're never quite sure where that where the plastic tube ends up as it goes down through the dipstick hole. And our sort of last choice again would be that drain plug for sampling from an engine. Let's get into a larger piece of equipment. So a hydraulic system, paper machine, large circulating system, a dry sump. So we have a reservoir that we in this system. So let me walk quickly around the system so we're all on board with it. Then we'll deal with some numbers here. So I got my reservoir at the bottom. I'm going to pull oil up through a pump, through a filter, and out through a series of bearings or gearboxes. Okay. So this could be, again, a paper machine, hydraulic machine. The oil comes back through return lines to a common return, back through a return line filter, and back into the reservoir. Over on the right side, we've got a kidney loop filtration system. We're coming up through a small pump, out through a fine filter typically, and then back down into the reservoir, just 24/7 cleaning up the oil. So let's walk through some numbers here. Let's just assume that in our reservoir, we've got 50 parts per million, and I'll just use iron as an example, as a wear metal here. We come up to our pump. This is a fairly large pump. It's going to contribute a bit of wear. So now we're up to 52 parts per million. This filter is probably not going to remove that smaller debris. Okay, the filter is probably coarser, maybe a 10 micron or beta 1000 filter, something like that. So we've got 52 parts per million up at the top here. That's going to come into all of our bearings. In a normal operating bearing, it still sheds off some wear debris. So our 52 plus 5 would give us 57 if we were sampling here. Come over to the far side, same with all these bearings. 52 plus 5 gives us 57. But in the middle, we've got a bad bearing. And it's going to contribute more wear debris. And I just picked a number of 15 parts per million. So my 52 plus 15 gives me 67 if I was sampling at this point. All these come back into a common header, and we're going to get the average of these bearings. So in this case, the number would come out to about 59 parts per million. We come back through a return line filter. Again, a coarser filter, probably not going to remove this fine debris, wear debris that we're seeing here. It's going to dump it back into our reservoir, okay, and mix with our 50 parts per million. Over on our kidney loop system, we're going to pull up our 50 parts per million, comes up through a small pump. This pump doesn't have a lot of volume to it, low pressure, so it's probably not contributing any significant wear. If we sampled here, we'd get 50 parts per million. We're going to come across a relatively fine filter here, because again, this filter is in here strictly for cleaning purposes, and we may remove some of that debris and knock it down to a much lower number. It drops it back into a reservoir with a much lower much lower iron content. If we sampled at this point, we might get a number sort of just again, a ballpark number of 20 parts per million, 30 parts per million. If we sampled off the bottom, we could get a higher number, 500 parts per million, because of the debris at the bottom of this reservoir. And every reservoir, every tank has debris at the bottom of it. Water, dirt, wear debris, spent additives, that kind of thing. So you can see that the numbers vary throughout the system. So we've got to grab a sample from a very consistent location. And I've mentioned here single primary sampling location. If my boss came to me and said, Bob, budget's tight, money's tight now, we can only afford to grab one sample a month from this piece of equipment, where would you grab it from? And my primary sampling port is going to be this one on the return line before the filter. Because one of the main things I'm looking for in my oil sampling is wear debris. And I want to capture that sample after it's gone through all my critical components, after my pump, which again is critical. So that's where the wear debris is most concentrated and before any filter has any chance of removing it. So that's my primary sampling port. So the concept is to monitor it, look for an increase in the wear debris. If I see a small increase, then that may be due to just one bad bearing in the system. Now, the theory is that you might be able to go back upstream and isolate that bearing or isolate a portion of the machine where this is coming from. Okay, so that's sort of the theory of how that might work. But there's our sampling port on our return line. Similarly, if we had a circulating system in a steel mill where we've got gearboxes, we've got a reservoir down at the bottom, we're going to pull oil up to a main oil pump, out to an oil filter, there could be coolers in here, out to a series of gearboxes, maybe in a steel mill where we're rolling steel. The oil is going to come back through return lines, back into our reservoir. Next here, we've got a kidney loop system out here that we're going to clean the oil and circulate it back into our reservoir. So once again, our primary oil sampling port, I would grab it from somewhere down in this area, again, preferably on an elbow, after it's come back from whatever number of gearboxes are in this system. So I'm sampling from all the gearboxes, looking for some initial increase in my wear debris before it dumps back into the tank. I really try to discourage people from taking reservoir or tank samples because all of our information gets diluted out. All of our wear debris gets diluted out into that large volume of oil in that tank. So there's our prime sampling port, again on the return line, before any filters and after all of our critical equipment. So very similar to the example we looked at just a moment ago.
Hi, Bob, can I interrupt you for a second? We
Sure.
have a couple of questions that have accumulated over the last few slides.
Okay.
And if we don't get to them all, we will get to them at the end of the presentation, ladies and gentlemen. But the first question is, in a large system, is it good to take the oil sample from the return line?
Yes.
Okay. And should it be after the pump or before the filter? Well,
it's in the diagram we have here. Here's our pump. It's pumped the oil up through the critical parts, components of our system. And so we're going to grab it where our information is most concentrated. There's an expression called maximize the data density. Get as much information into your sample as possible. So after the critical components, before the filter, on the return.
Okay. Here's an example. What is the best sampling point for a reciprocating engine, i.e. gas engine and diesel engine? Any difference in that?
Well, again, as we said here, when we talk about engines, trying to grab a sample off the filter housing. And that's after the pump, before the filter. So that's sort of a prime sampling port.
Okay.
Now, you may not have a filter housing that has a sampling port built into it. So you could either retrofit one to that particular engine, or second choice, the plastic tube down through a dipstick hole or a vent.
Okay, and then are you able to extend the oil change period in either the gas engine or diesel engine application through oil analysis?
Well, you may be able to. It depends on what your results are. If you've been doing oil analysis strictly on a preventative basis, on a time basis, you may find that if you go to oil analysis, you may find that you've been changing your oil prematurely, and you may be able to extend your drain intervals. But it would depend strictly on the results. Now, one thing I would always caution people about is if you're extending drain intervals, do it slowly. Let's just take an example here of a gas engine, a natural gas engine that maybe the drain interval is 1,500 hours. I would never extend that suddenly up to 3,000 or 4,000 hours, double or triple it right away. I would take it up in increments. I would go from 1,500 hours up to 2,000 hours. Let it run there for a few months. Check my samples. Is everything still okay? Then go from 2,000 to 2,500. I walk things up very cautiously just to be sure that I haven't overlooked something and made a mistake. But yes, you can extend your drain intervals by using oil analysis and getting good samples. And again, key to oil analysis, good samples. If it's a garbage in, garbage out scenario, and I realize that's a phrase some people may not be familiar with, but if you get a bad sample, a non-representative sample of oil, you're not going to get representative results back, and you're going to make some wrong decisions. So the sample's the very front end of oil analysis. You've got to get the sample done properly, or nothing can correct that afterwards. Everything after that, all the analysis is a moot point, is irrelevant if you've got a non-representative sample.
Do you have any feedback, or what would your position be on equipment that is almost permanently in standby condition? In the standby condition, would you change the interval of oil analysis, or what would the frequency be of a standby machine that's not running?
For sampling. So many plants have emergency generators or fire water pumps that have diesel engines. Those engines should be fired up and run at least once a month and for a couple of hours to get the oil circulated, get the engine up to full operating temperature, and so that we drive off any moisture that's maybe accumulated in there. And it also, again, rotates the shafts, the bearings, so that they're not, when it shuts down, it's not sitting on the same position constantly, because then you'll get a weird phenomenon called fretting, false Brinelling. And sorry, repeat the question again, Peter, just so I'm not going off on a tangent.
Oh, no, that's fine. I think you've answered it, actually. The question was, if the engine is not continuously running and always in standby condition, what will the frequency of oil sampling be?
Right. So this engine's probably, well, this piece of equipment's not getting a lot of hours on it, but you're starting it up occasionally. I would certainly, there's no point in sampling it every month. As we get further into this course, we're going to see that monthly sampling is very common for industrial equipment. So if it's only being started up and run for a short period of time, just to, again, get the oil circulated, sampling it monthly would be pointless. You're not going to get any change in your results. So if this was in long-term sort of standby, like a fire water pump or emergency generator, I would probably only be sampling it yearly, something in that sort of time frame.
Okay. Please continue.
Okay. Again, that's a personal opinion. I may get some disagreement from people on that, but I just can't see sampling it every month. So we were talking about this gearbox system in a steel mill or something like that, where we've got oil circulating out to a large piece of equipment. And my next comment was sampling from a permanent kidney loop. So we had taken, let me just back up for a second. There was our primary sampling location here. But if we've got a kidney loop and you were going to sample from that, taking oil off of here, you want it again after the pump, before the filter. So that's a classic way to remember where to grab samples off of small circulating systems. And again, on an elbow. So again, from a permanent kidney loop, that's where you'd want to grab your sample. If we're taking samples from a reservoir or a tank, and my first comment is avoid tank and reservoir samples. They don't mix consistently, so the oil's not uniform in that tank. So I prefer to not take a sample from there. But if I have to, if I've got no other option, I prefer to try to get the sample from the middle of the tank or a fixed distance off the bottom. Stay away from the bottom where there's sediment, stay away from the walls, stay away from the top. Try to grab it in the middle of that oil reservoir or sample. So here I've showed a plastic tube that we've zip tied or tethered to a rod. Again, no pressure in the system, so I have to pull a vacuum to pull my sample up, but I want it at a constant depth in here. So as one person said to me, you could put a collar on this rod so that when you put it down through the opening, it will only go to a certain depth every time. I don't want to put the rod against the bottom of the tank and dislodge, disrupt any of this sediment at the bottom. Because if the rod goes down and plunks against the bottom of the tank, some of this debris is going to get circulated up into the oil. Then I start sucking it up into my tube, and I could get some of that into my sample bottle. So again, I'd like to let the debris at the bottom sit there and not cause us any problem. So again, a fixed distance off the bottom, a collar on that rod would accomplish that.
Bob, may I interrupt you on the plastic tube?
Sure.
How do you know if it's clean or when to replace it, or should you use that plastic tube for multiple machines?
I would flush the tube, and I would use if you were sampling multiple pieces of equipment, use a fresh piece of tubing each time. I've heard examples where a laboratory comes into a plant, and so as a lab employee comes into the plant, he's walked around, and the lab actually takes the samples, and it was mentioned to me that he used the same piece of plastic tubing all day long, and I would avoid that because you're going to get cross-contamination from one sample into the next. If you've pulled a thick, heavy gear oil up into a piece of plastic tubing, you would have to flush a lot of ISO 32 hydraulic oil or turbine oil through that tube to get all that thick gear oil off the walls of that tubing. So I would just cut a new, fresh piece of tubing each time.
Question, why we cannot take oil from the top of the reservoir?
Just that you might be getting a better than, what's my right terminology? You might be getting a best case scenario, taking some samples right from the top, especially if there's not a lot of agitation in this reservoir. Drums are a problem, I made a huge mistake years ago. We were out sampling some drums, and it was a lot easier for me to put a small piece of tubing onto my vacuum pump and pull a sample from the top of the drum to check cleanliness and quality of it. And all the results came back really nice. They were a nice, clean oil. But afterwards, reflecting back on what I'd done, I wished I had taken either a mid sample of that drum or maybe even 3 samples, top, middle, and bottom, to see if there was any stratification. But I was concerned that by taking a top sample, same thing with this reservoir, taking a sample at the top of it, you may not get a representative sample. It might be cleaner than the average cleanliness of that oil.
Okay, please continue.
Okay. So here we've got a reservoir that doesn't have a baffle in it. I'm going to add an example here where, say, there's a baffle in this tank or reservoir. And we've got a return line over on the left-hand side, putting oil back in. There's our vacuum pump that we're going to pull our sample up into our bottle. But we've got a baffle here. And I've read from a couple of different sources that you want to grab that sample on the same side of the baffle as the inlet oil is coming back in, not where the oil is exiting. Because, again, most of the debris over here is going to be in this area. You would get a cleaner than expected sample on the other side, or at least understand where you're grabbing your sample from in this reservoir. Because you could pose the argument that, well, this is the oil that's actually going out into my piece of equipment, so shouldn't I grab a sample on the right-hand side where it's labeled as unacceptable? I think both could be valid. You could take a sample on either side of that baffle, but at least understand, where did I grab the sample from, and what is it a sample of? Is it a sample of the outgoing oil, or is it a sample of maybe the wear debris coming back in? Let's talk about we're headed towards frequency of sampling here. I'm sorry, our time is moving on here, so I'll try not to waste too much time here. I wanted to make a comment about sampling industrial equipment versus mobile equipment, engines basically. At the top here, we've got industrial oils, stationary engines, equipment like that. We're looking, I've plotted on the vertical axis, I've plotted this could be acid number, viscosity, an infrared measurement, it could be wear debris. And then we've got time on the horizontal axis. So what I wanted to point out here is each one of these dots is a monthly sample, and usually we're taking several samples, multiple samples, during the life of an oil fill. So all of these samples that have been taken here are on the same oil fill. There is no oil drain between any of these samples. And this is going to get important when you look at your oil analysis results. So you need to differentiate an industrial piece of equipment, a hydraulic system, a turbine system, where the oil is let me word that differently, where the samples are from the same fill of oil, as opposed to down on the bottom, an engine oil, mobile piece of equipment. You may take a sample of your brand new oil, and I've mentioned a base number here, so it's a higher number to start with of the brand new oil. The oil goes into service, the base number comes down, we take a sample typically at the drain. But so this is one fill, so there's one sample of oil taken for each fill of oil. Then there's an oil drain, and we start this process over with an engine. So let me show you an example of just some data to illustrate this. So this is some engine oil data, and the reason I know that is if I look over at my additive elements, my calcium, zinc, and phosphorus, I can see that I've got quite a bit of calcium in here. This is the detergent additive. Looks like it's up in the 1,500 parts per million range. Zinc and phosphorus are the anti-wear, phosphorus anti-wear additive. And again, so right away by looking at this, I can see this is an engine oil that I'm dealing with. Now, because it's an engine oil, let's look at the samples. You need to look at the dates on the samples to know which way to read the data. What's your oldest sample? What's your newest sample? So in this particular format, they're reading from bottom to top. And with an engine, I can say with a high degree of confidence that each line of data across here is one oil sample from one fill. So after this data was generated, there was an oil change. Then the next data was generated on the next oil change. Third oil change, fourth oil change, fifth oil change. So let's just look at the iron numbers quickly here. And I don't want to get into a bunch of interpretation of data, but just to illustrate how understanding how the samples were taken and relative to oil changes. So this piece of equipment, this engine created 5 parts per million of iron during one oil change. Let's say it was 300-hour interval. The next interval, 300 hours, it created 8 parts per million. 8 parts per million again on the third interval, and an oil change again. Now we're up to 13 parts per million in a 300-hour span, and this again is a separate oil change, and 13 again. This is a pattern illustrating that the wear is increasing. This is a bad pattern, a negative pattern. We're showing that this engine is wearing more and more with time. Remembering that each one of these pieces of data is on an individual fill of oil with an oil change afterwards. Now, what if I saw this same data from a turbine or hydraulic system? That would mean that this oil was taken month after month, but it's the same oil fill. So during the first month, 5 parts per million. So after the second month, 8 parts per million, 8, 13, and 13. That would be a very typical pattern, because you'd expect wear debris to slowly build up in your oil because there are no oil changes happening here. And this wear debris that we're seeing here is probably quite small. That's why it's being picked up by the elemental analysis. So it's not being removed by a filter. And so you expect it to increase. So this pattern of numbers would be horrifying in an engine, but quite common and normal in a hydraulic or turbine system. I just wanted to illustrate that to you. Let's talk about some factors that affect our sampling frequency. The criticality of the equipment. How critical is this piece of equipment? And this usually ties back to dollars. Is it making a lot of money for you? Is it critical to the operation of your plant? If this piece of equipment failed, would it shut down your plant and impact your production? So again, more critical the equipment is, the more frequently we can justify the cost of taking more samples. Budget and manpower are going to be huge factors in how often you sample. If you sample monthly versus every 2 months or 3 months, if you back that off to the 2 or 3 month intervals, you're going to save money because it's going to take less manpower to take these samples. You're going to be doing less oil analysis, so it's going to be lower cost to you. Now, there's a risk at that of taking samples less often, and we'll get to that in a second. Environment. If you're in a dirty, wet environment, you probably want to sample more often to, again, keep closer ties, closer track of what's happening within your equipment. As the machine ages, older machines starting to wear is increasing, we probably want to sample more often, again, to keep closer track of how quickly this piece of equipment's coming to a failure. As our oil ages, we want to sample more often. So as my acid number, infrared oxidations start to go up, I may want to sample more often than just monthly, again, to just keep closer tabs on the data and how close I'm getting to having to have an oil change. I've showed a PF curve here, and I don't want to get into this in great detail because we could spend a whole bunch of time here, but a PF curve illustrates how a failure occurs, how it progresses. So on the vertical line here, the y-axis is basically the performance of a piece of equipment. On the horizontal axis is time. So let me go back up to the start. So we've got a new piece of equipment here. It's operating properly. And eventually, sorry, something just fell over here. Eventually, our piece of equipment starts to wear. So failure inception starts. But it hasn't, the performance of our equipment has not decreased to the point where we can actually detect that yet. As we keep coming across and the failure progresses, we get to a first point of detection of that failure, and we label that P. As the failure keeps progressing, the performance of the piece of equipment keeps deteriorating, we now get to a point we refer to as F, a functional failure. The equipment now cannot perform the function we need it to perform. If it was a pump pumping a fluid, a liquid, now we're below the threat. We hit the minimum threshold of flow that we require. Now the pump is still running, hasn't catastrophically failed yet. That's down at the end here. So we have this time interval between P and F, and we want to try to grab samples between that. So I've indicated down here, if you were taking samples on a monthly basis, we've come along. So far, nothing's been detected. Probably at this sample, nothing's been detected. And our first sample, where we start to detect our failure, so first sample after P, sorry, it's hard to keep this in a straight line, would be this sample right here. So in the above example, as we keep progressing across here, I've indicated that the time to get to F, in the example above, the PF interval is approximately 5 months. You want a sampling interval that should not be greater than 50% of the PF interval. Now, PF is not known. We don't know exactly how long this failure is going to take to progress, but we want to take samples often enough that we catch the failure. And we prefer to catch it as soon after P as possible so that we have more time to plan for the eventual failure of this piece of equipment. And I always say to people, if your sampling interval is out as far as 6 months, so you're trying to cut down on your cost, you're only going to grab samples in 6-month intervals, you could potentially miss this failure. Now, there's some conditions on this. There's a bit of a caveat here because in large reservoir systems, turbine systems, you may only sample 6 months, every 6 months because things don't change much with that much oil volume. If you've got tens of thousands of liters of oil, you may sample far less frequently. But on smaller sump systems, I usually say to people, monthly is your starting point. If you want to try to cut your costs, back off to 2-month, 3-month intervals. But by the time you're out at 6 months or a year, I'm starting to question the value of that in an oil analysis program. Now, in this next slide, I've walked through that. I'm not going to read through it again, but hopefully if you were looking at this in the taped version, you could pause it on this slide if you wanted to read through what I've said again. So sampling frequency, just a bit of a review here, somewhere between 2 weeks and 3 months. Quite often the default is monthly, and some people 500 hours to 750 hours. I think if you average all the months, it's about 730 is the average for a month. So that's sort of a standard for industrial equipment. And again, repeating what I said before, you could reduce this to from 1 month to 2 or 3 months. That's going to reduce your cost, but realize you're accepting more risk because you're now not sampling as often. You're going to get less information less frequently. Industrial gas turbines, I believe, due to ASTM documents, they talk about sampling every 500 hours. Diesel engines every 250 to 300 hours, again, for typical off-road. And again, you could calculate that out for on-road if you wanted to do it. Those are very typical numbers. So if in some cases, if the duty, the stress on the engine is lower, lower loads, you might be able to extend this out to 500 or even 1,000 hours on some light-duty diesels. So let me go back. One point I wanted to make today, and I'm sorry we've hit our hour time frame. If anyone has to leave, I apologize for running over here. But this is being taped, and again, you'll have access to the second half or the tail end of this later on. But let me just talk about sampling and oil changes, because I've seen some information here that's confusing. So I'll go back to my diagram I said before. We take a sample of our brand new oil, then we take samples maybe on a monthly basis. We see our results going up, whether it's wear debris or acid number, and we try to target an oil change. We try to get as much life out of our oil without doing any damage, and we try to target an oil change right at that last sort of before this gets very, very steep and our acid number or our oxidation gets very high. So sampling, my comment here, sample at the oil change to collect data from the previous sampling period. I've talked to some people who operate mobile equipment and mining operations, and they say they take a sample maybe about a week before scheduled maintenance so that they can take that sample off of an engine or a transmission, get it analyzed, so when the truck comes into the shop for maintenance, they have that information available to them so that they have an idea of whether there's something they need to address while this truck's in the shop. A glycol leak, excessive wear in the engine, something like that. So that's a sample right at the end. We talked earlier about sampling brand new oil, so sample new oil going into the equipment. This acts like a quality check, and it also provides a new oil baseline, so again, grabbing that sample. And another one that I like to take, and this is the one that I've seen people say, there's a bit of controversy about this, but sampling 24 hours after an oil change. And ASTM actually recommends doing this because now what they're allowing is the new oil to mix with any residual oil, and this is actually going to give you a better baseline for trending. So if you took your brand new oil out of the container, it might have lower wear, it would have lower wear metals, acid number, viscosity, infrared numbers. But as soon as that oil's gone into your system and mixed with any residual oil, the wear metals are going to go up. Acid number is going to go up slightly. Viscosity may go up slightly because it's mixed with older oil. So this is actually a better baseline than the new oil value. Okay, so that's an option to take that sample and use that as a better baseline for your changes going forward. One more thing I wanted to mention here, should oil be topped up to a consistent level in the sump or reservoir before sampling? Okay, best practice would say yes, it should. You should top up the oil. So again, we're dealing with, the same volume of oil constantly in our sump or our reservoir. But if you're going to do that, now you must allow for the makeup oil to mix completely before sampling. So you don't want to just pour the fresh new oil in, makeup oil, and sample right away. Allow it to mix, and that could be 12 hours, 24 hours. And you also want to make a note of how much oil you've added so that you can correct for the dilution effect you'll have on the data. And there's an equation down here at the bottom that I've provided for correcting for it. So here's your value from the laboratory, say your parts per million of iron, and based on your sump volume and your makeup oil, that will actually knock this number back and give you a corrected number for the dilution effect. Now, this is a very simple equation. There's more complicated ways of doing it, but this actually does a pretty reasonable job of correcting for that wear debris and the dilution that's happening. Okay, so something to think about. I want to just walk through a couple of tips here and one final story at the end. So this is kind of repetitive of what we've said before. I want to follow a written procedure for consistency. I want my samples taken the same way every single time. I want to sample the equipment while it's operating so that I'm getting a representative sample and it's being mixed. So allow the equipment to run for at least 10 to 50, 50 to 20 minutes before sampling. And again, a sample before or during the oil change to capture the data, or immediately after it's shut down. There might be safety reasons why you can't grab a sample while the equipment's running, but again, be very consistent. Use clean bottles. We talked about that. There's different cleanliness levels. Again, some tests require a larger volume of samples, so you may need 2 sample bottles to collect enough volume for your lab testing. Do not expose the lab to any airborne, do not expose the bottle to any lab, I'll get this right. Do not expose the bottle to any airborne contaminants. So there is a method that's sometimes illustrated where you can use a plastic Ziploc bag to put the sample bottle in a dirty environment and then thread that up into your vacuum pump. That's going to be awkward, but some way of trying to keep airborne contaminants out of your sample bottle. Want to be consistent. We want one primary sampling port. You may have multiple ports on a piece of equipment, but you want one main sampling port. Remember that the amount of wear debris varies throughout the system. You want to flush your sample valve, flush any tubing. A rule of thumb is to know the volume of static oil in your tubing, in your equipment, and flush 5 to 10 times that volume to be sure that you're getting a representative sample. Use a new piece of tubing every time you take a sample. We talked about that. Do not completely fill the bottle. Again, rule of thumb is to fill it about 75% full. Get the lid on that bottle as quickly as possible so that we don't get any airborne contaminants in it. Label the sample properly. Be sure you've got the right equipment number. That's absolutely critical so that your data, when it goes to the lab can get your data from that sample assigned to the right piece of equipment. The oil type, the oil grade, the date, the plant it's come from. It certainly helps to have the hours on the oil if you know that, because now we can sometimes correct our data. We can normalize it for the number of hours on the oil and actually calculate a wear rate, but you need the hours to do that. Many times there are no clocks on equipment, so that information is not known. It also can be helpful to know if the machine's currently in service, if there's any visible material in the sample, any smell, was a filter card or a vacuum dehydration unit used on this sample beforehand to remove some debris, and was the oil and filter changed after the oil sample was taken. Get the sample into the lab as quickly as possible. Again, we talked about sampling intervals. Monthly is kind of a rule of thumb. Try not to sample simply based on a computer-generated system where you sample on the first day of the month regardless of the operating hours and condition, not immediately after adding a large volume of oil, or not during an idle period or temporarily out of service where that equipment's just sitting there. I've given you a procedure here for sampling. I'm not going to read through this, but again, hopefully if you want this, you can pause the tape of this and write this down or jot it down. It did come from a NORIA publication. I've given you the date down at the bottom. So we talk about the preparation for taking a sample, flushing before a sample, and on the next page, actually the sample itself. Now, I would expect anybody looking at this to, this is a starting point. It's a template, and that you would alter this for your specific pieces of equipment, and that you'd have a procedure for each individual piece of equipment in your plant, so that everyone has a written procedure. Everyone that's going to take a sample does it exactly the same way every time. And there's no dispute about how it's taken. This is how we take samples. Now, this can always be changed. If somebody comes up with a better idea, alter your procedure. It's not cast in stone. You can change this at any time and update it for a better procedure. But you need a procedure for each individual sampling port so that if you've got 2 or 3 people taking samples, they're doing it exactly the same way every time. Otherwise, you're going to have inconsistency in your results, and you're going to have trouble getting consistent results and meaningful data. And one last comment here. This was sampling from a mining shovel. And there's something here I just wanted to point out to you, and it, again, is related to sampling interval. So this was sorry, I'll just take you down to the bottom here. This was in a NORIA publication, a Machinery Lubrication magazine in April 2017. So you can go back into Nordia's website, nordia.com, and find this article. But here's the summary of it. It's a mining shovel. It's a track drive system on this that moves it back and forth. And the track system is propelled by gearboxes. Normal procedure here was to take a basic oil analysis sample every 3 months. They weren't taking any reference samples, any new oil reference samples. And the approach was to replace the oil every 6 to 12 months. Problem occurs. They're failing these gearboxes every 6 to 8 months. Okay, at $400,000 for each gearbox, plus cost of labor, plus cost of lost production. So this is becoming an expensive proposition. So to try to make a long story short, somebody decides that they're going to take an oil sample 2 weeks after they've changed the oil and the gearbox. So brand new gearbox is installed. They put fresh oil in it. Now, instead of waiting for 3 months to grab their first sample, they're going to grab it after 2 weeks. What they find is that the determination determines that the phosphorus EP additive in the oil has depleted. So the phosphorus level might have started off at 500 parts per million, 3 to 500 parts per million of phosphorus in their gear oil. They go back 2 weeks later, and the phosphorus is essentially down to zero. Well, where did it go? It plated out on all the raw new metal surfaces within the piece of equipment. It was basically pacifying the surface of all that raw steel in the gearbox. But now there's no reserve left, and this is causing their failures. So I wanted to point this out to people because I think this probably happens more often than we realize. We install a new piece of equipment, and it could be in a plant. It could be a gearbox in a plant. It could be a hydraulic system. And if there's a lot of raw steel, the additives will plate out. Some of the EP additives, rust-inhibiting additives, come out of the bulk oil, plate out on the metal surfaces, and pacify the surfaces. So now the oil, the bulk oil, is depleted of those additives. It needs a short oil change or a quick oil change to be sure that those additives get replenished in there. So what they revised the procedure to do was they upgraded their sampling analysis. They also included ferrous density, another pet peeve of mine that we don't do enough ferrous density testing. This is looking for large iron in gearboxes and is very indicative of catastrophic or severe failures. So they decide they're going to do this sample every 2 weeks. Replace the oil after 1 month initially, and then replace it every 3 to 4 months. So again, they're doing short oil drains initially. This flushes out initial wear debris and contaminants from the piece of equipment and replenishes additives. These guys at this particular mining operation in the U.S. did this. Failures stopped happening, and they saved millions of dollars. So that takes me to the end of this presentation, and I'm sorry it's run 15 minutes over. Hopefully that was worthwhile to spend that bit of extra time. Peter, any questions? Peter, any questions?
Sorry, Bob. We will answer as many questions as we can in the next 10 minutes. We have a few. And I'll just start with, can you share your opinion, Bob, regarding oil samples from filter drain points? Is that acceptable?
I'm not sure what we're referring to as a filter drain point.
Well, the filter drain point would typically be the dirty side of the filter.
Okay, so you're on the upstream side of the filter, and you've got so you've simply got a drain plug or something on the upstream side of the filter, and you're going to grab a sample from there.
I guess my concern would be whether it's turbulent flow or not. If it's just been sitting there accumulating, might not be representative. But what are your thoughts on that? Well,
we want to grab samples from the dirty side of the filter, the upstream side of the filter, because the filter maybe, especially depends on its micron rating, could be removing some of the debris we're looking for, so we want to grab it upstream. But we want to be sure it's a representative sample, so we want what is commonly referred to as a live zone sample, so that they've got flowing representative oil and that it isn't stagnant oil that's been sitting there since the last sample was taken.
Yeah, like so the equipment's running. It's not like a filter cart that was disconnected a month ago and just sitting idle there. It would have to be an operating machine type of thing, right?
Right, and then taking a sample there would be quite valid. But again, be careful. We don't want to be taking samples from stagnant pieces of piping. And again, we talked about that. Flushing, be sure if you've got a stagnant length of pipe, know the volume of oil that's stagnant, that's sitting there, and flush 5 to 10 times that volume out and discard that before you grab your sample that you're going to send to the lab.
Okay. We have another question. One of the major OEMs of medium speed engines suggests to take the engine oil sample after the filter, but before the engine inlet. Is that the right approach?
Again, as long as you understand what you're looking for. So in doing a sample after the filter, before it goes through the critical part of the equipment, you're essentially taking, I'm using some new terminology here, but a proactive sample. Can I just bounce, I'm just going to bounce back
Sure.
and see if I...
Sure.
Okay, so taking a sample up in this area, okay, let's assume this is an engine, okay, because they refer to engines. So the same thing happens. We've got a pump, we've got a filter, and they want to take a sample after the filter. So what they're really doing is they're monitoring the cleanliness, water content, wear debris of the oil going in to the piece of equipment. You could refer to that as a proactive sample. You're trying to be sure that the oil is clean and dry going into your equipment. But you could be missing some wear debris that filter has taken out. And so one of the reasons we want to grab a sample after the pump before the filter is to look for wear debris. So it would depend on the size of that filter, meaning its micron rating and beta ratio. Is it going to be touching any of the wear debris we're looking for? Because again, you'll if it's removing it, you're not going to find it downstream in the filter. So as long as you understand what this sample is by taking it up here, and that you may not see wear debris coming off of your engine up there, because the filter might be fine enough to remove it. Now, many engines don't have very fine filters on them, so a lot of that wear debris will go through that filter.
While you're on that slide, Bob, you have an elbow here, and the question is, wouldn't that be a problem for an area where debris would be collecting?
My understanding is exactly the opposite. It's going to get turbulent flow as the oil makes that right angle turn and get better mixing. Okay. You're more likely to get laminar flow and sediment happening in a straight piece of pipe.
Okay. I have another question. Is there any documentation mentioning condemning limits for parameters like wear metals on the different?
Absolutely.
Yeah, is there?
Absolutely. All kinds of information on condemning limits for all different parameters, whether it's infrared information, acid numbers, base numbers, viscosities, wear metals. So there's some general rules of thumb for different types of equipment, hydraulics, gears, bearings, or something specific from the OEM for a piece of equipment.
Is that something you could send to me and I could forward?
I've got some general information I can.
Okay, that'd be fine. Question.
There's thousands of manufacturers of equipment, and I just don't have access and would not even want to.
So, you know what? Well, why don't we just back up then? I guess it depends on the piece of equipment, the application, and the manufacturer of that device, right? And your first resource would always be, what is the specification with respect to oil and contamination levels for that machine? Reach out to those manufacturers, and then perhaps also as a great resource would be your oil supplier. Your oil supplier would be in an excellent position to be given some guidance on what the contamination level maximum should be for that machine, correct?
I would put more weight on the manufacturer of the equipment, his information.
Okay.
He's probably got more information, or even oil analysis labs. If oil analysis labs are seeing a lot of a certain type of equipment, they will be able to statistically look at the data that they typically get and know what is a normal result for that piece of equipment. And lots of labs now are using graphs, plotting the data with graphs and showing where the statistical standard deviation, first, second, third standard deviation of the variation of the data and what's acceptable and not. Lots of labs are doing that these days. So the lab with the OEM would be my first place to go.
Perfect. You showed a number of examples, Bob, where you're using a plastic tube to take the oil sample. The question is, are those tubes used to take samples from operating equipment? Is there any concern about that plastic tubing getting sucked into the gears there?
Absolutely. And I recall saying that one of the problems with using this plastic tube method is you're going to have to shut down the gearbox. And we prefer to take our sample with everything operating normally so we get a better, more representative sample. So again, by taking, I'm just pointing to this one gearbox with this fixed piece of rigid pipe that's sitting in the same place every time, not interfering with the rotating equipment at all, that's my first choice for grabbing a sample.
I'm not going to slightly different direction on the next question, just from your expert opinion. Is there any way to improve the flash point of a lubricant running in a gas compressor? In the situation being presented, the gas compressor is critical for production right now with COVID-19, and they're wondering if they can do anything about trying to improve the flash point of that oil.
So trying to drive off, the flash point's probably decreased because there's light ends getting into the oil. That's what I'm kind of reading here. Compressor, I believe.
Yeah, a gas compressor.
I've got to think that there's technology out there to do that, Peter, but I'm not familiar with it, so I'm reluctant to say specifically.
Well, I'm going to just chime in here a little bit from my side, is that it's a very unusual test. A flash point is something that's done when there's an extreme risk of fire, or most often when you purchase the lubricant, or if the lubricant manufacturer, say, is running a supplementary test on an annual basis. You do need to look at the variability and the ASTM accepted variability in that test method. And if it was confirmed to be low and there was a risk of fire in this application, and it was a significant deviation that concerned you, you could always do a bleed-in feed to some degree to boost that flash point. I mean, if that machine cannot be shut down, you can always do bleed-in feeds to try and improve some of the properties.
Peter, I've got to think that there's technology out there for, so let's say in this compressor, a normal flash point of a lubricating oil might be something, I'm just going to pick a round number, 250 degrees Celsius. And I'm in the ballpark, it could be 230, but let's just say 250. And it drops down to the low 200s, 210. You've probably got some hydrocarbons or something's pulling that flash point down. There's still no risk of fire there, but you've got an indication that you've got contaminants into that oil. And I've got to think that there's technology out there that would take that oil, a side stream of that oil, and be able to remove some of those lighter hydrocarbons. Heat them and take them off, or pull a vacuum on it and pull off the lighter hydrocarbons and pull your flash point back up. I can't. I would expect the technology to be there, but I can't think of a specific piece of equipment or a company that manufactures something like that. But it's got to be out there.
Okay, excellent. We have a couple more questions, and then that's the end of them.
Okay.
Have you ever made an oil sample? Have you ever taken an oil sample from a refrigerant screw compressor?
I have very limited experience with refrigeration systems, so I'm going to answer that with a no. And we had this type of question in one of our previous sessions, and one thing I found with a lot of industrial plants that I've dealt with, they contract out the refrigeration systems because it's so specialized. So they'll hire in a contract company to come in and do maintenance, oil sampling, and that on their refrigeration systems. So I just have had almost zero experience with them. So I'm going to default on trying to answer that.
And the second part of that question is, what do you do if there is really not an appropriate sample point? Any thoughts on that?
Install one?
Is it difficult to install one? Is that something that you can add to your equipment? Is that frequently done?
Yes. So let me just sample here. So again, this piece of equipment probably didn't come with a sample port in it. And during some outage, when this equipment was down, they've opened up this line and put this sampling port in here. So it's been retrofitted in afterwards by the maintenance crew.
I have a comment back. For high flash point applications, try using synthetic lubricants. That was just a comment in general of one option that could be considered. And then, do you have any comments on that, Bob?
Well, certainly the synthetic oils are going to have a higher flash point because they don't have a mix of different sized hydrocarbons in them the way a conventional mineral oil would. So they'll start off with a slightly higher flash point for sure. But I think the question that was asked is, if the flash point comes down, is there something I can do to treat it to get that flash point back up? So the synthetic would have the same problem. It may start with a higher flash point, but if it comes down and you want to try to remove the lighter ends that have contaminated it, you've still got the same problem.
Yeah, I was just thinking a little bit differently along those lines, but in applications where you couldn't shut the machine down and you had some concern with flash point, a partial mitigation could be to potentially put a nitrogen blanket on that system to take away any oxygen from the equation. That might offer some additional protection, but again, check the flash point itself. Check with your oil manufacturer. This is a very specialized test. We see very, very few of those done.
One other comment, Peter. I still don't think the flash point is going to get low enough that it could be a safety hazard. But remember, if the flash point's coming down because of contamination with a lighter product, your viscosity is going to come down. Now you've got my attention because the viscosity coming down, I'm going to start having oil film issues and metal-to-metal contact.
Well, I have a question from the audience here. It says, we are using synthetic oil in our gas compressors, and after running this for almost 2 years, we're facing issues with flash point. Would just like to share what we are doing is to top up the agreed percentage of oil after some time and take another sample to prove the flash point has increased. So that's just a comment from the audience.
Okay, that sounded like almost a bleed and feed.
Bleed and feed. And you'd be surprised. I've been at nuclear power plants when there's been a critical failure and a shutdown, and the plant has no replacement oil on site. And I always just shake my head and say, how is that even possible at a nuclear power plant in a specialized application? Always have replacement fluid available. In a catastrophic situation, you should be able to do a 10 or 20% bleed and feed of your lubricant system. It is an effective strategy in some situations where you can't shut down. Another comment, refrigeration compressors having pressurized lube oil system, and the sample point is the discharge of the pump before the filter. Okay, just as some advice on where you could install a sampling point if there was not one there in your refrigeration compressor. They said it's been very effective for them so far.
I would always have some oil on hand. Have we not learned this with this COVID situation of having PPE and storage on, for when you need it? The whole concept of just-in-time delivery, only having in stock what you absolutely need, that's fine as long as everything's working well. But when things start going wrong, suddenly you're going to want some spare oil, you're going to want some spare PPE around. And I think we've learned that the hard way.
Well, okay. Well, I apologize for the password situation today. I don't know what happened. We were into the webinar settings, and somehow that must have been selected. And we'll work on that for next time. But normally, no password is required to enter these meetings. We will provide a complete recording of the meeting for all the registered attendees. Oh, and we have a couple more questions. Just again, getting back to that question, a comment. For a screw compressor in the gas refrigeration service, the in-service diluted viscosity needs to be calculated based on operating temperature and pressures, as well as gas analysis regarding the flash point. Just for the discussion, it says.
Okay.
Okay, and they're responding back and forth to each other right now, so that's great. Yeah. Last question, please. Okay. Do you require an oil change on time base for engines if you're doing oil sampling? In the case of the mini shovel example you provided?
Do you require an oil change on a time basis? For a lot of mobile equipment, it will be done on a time basis. Okay, I'm not sure which way to go on my slides here. Oh, I'm likely going the wrong way here. Let's look at our mobile equipment down here. We've done so many samples on engines and mobile equipment. We know that it's very likely going to take 250 to 300 hour oil drain intervals. We just have so much information on typical diesel engines. Okay, so we're basically doing it on a time basis for oil changes because we have information. Now, if you found that your oil was still in really good shape after that period, you might want to try to extend it out. And again, any extension of oil drains, do it cautiously, do it slowly. As I said before, if you're at 300 hours, maybe move out to 350, 325, see if everything's still okay. And then keep extending and again, checking your oil analysis data. So we are doing it on a time basis, and that would be the same again with a lot of mobile equipment because it's scheduled quite often to come back into the shop for hydraulic systems, transmissions, engines, for maintenance on a timed clocked basis. I would certainly just add to that, in an industrial environment, we should be moving away from doing time maintenance on equipment and doing it based on condition, doing it based on predictive information from vibration, oil analysis, thermography, motor current analysis, ultrasonics, those 5 technologies to help us monitor the equipment, monitor the oil, and do our maintenance based on condition of the equipment and the oil as opposed to time.
But you can combine strategies for preventative maintenance and condition-based maintenance as well, right?
Sure.
Like, yeah, it depends on the application. We're going to wrap it up with this last question. It's a really good question, and because I've seen it myself. You go into the oil room at a company, and they have all their sample containers there for doing oil analysis, and they're never sealed. The lids are in one bucket, and the containers are in the other bucket. What do you think about that, Bob?
So these are your oil sample bottles?
Yeah, before they're used.
They're useless.
They're useless.
Now, okay, that's my first comment, but okay. If you're going to do testing where you're doing particle counts, if the bottles come with the lids off, the sample bottle is useless because that bottle has now become contaminated with airborne contaminants. If you were simply going to use that bottle, the lid's off of it in the cardboard box, you open it up, lids are off, and you're simply going to use that for something like a viscosity, you're probably okay. But that's unacceptable because the lab, who's sending these bottles out, or the manufacturer of the bottles, these should all be sealed. It should be a bottle inside another bottle, all the lids on tight, so that your sample bottle inside is the correct cleanliness that it was manufactured to.
And from your understanding, is that the way the sample bottles come from the manufacturer?
Yes, it should be sealed and cleaned and sealed, lids on.
Okay, well, I'd like to thank our participants for their attention and the great dialogue we had with the many questions. So that's been really good. And I'd like to thank Bob for giving us all his energy and time today. And if there's any remaining questions, you can contact us via email and we'll try to accommodate your requests. So thank you very much. A recording of the presentation will be available in 2 days. Unfortunately, it's not available for 2 days because WebEx takes 2 days to do the encoding and compression, and then I get a notification that the recording is available. The moment I get that, I will send it to all registered participants. So thank you, and we look forward to you attending another one of our webinars. Thank you.
Okay, thank you, everyone.